So this is a video solution for problem 13 on the momentum test review. Some of you guys had asked for help on this one, so here we go. It says, at a ballistics lab, a .1 kilogram bullet is fired horizontally from a 1 kilogram gun held by a 79 kilogram person into a 5 kilogram block of wood resting on a table. The bullet embeds itself in a block of wood, and the bullet and block slide backward at 3 meters per second immediately after the collision. Okay, now several of you said, I just had no idea figuring out what was going on with this. Well, that's really, like, not to be harsh, but that's not an excuse. That's okay, well, if you don't know, draw a picture of it. Like, start to draw a picture of what you think is going on. So that's what I did. So here's my picture. I've got a bullet. I know it's going to fly and it's going to hit a block of wood. These are the things I know about the bullet. Okay, it's mass, and I don't know how fast it's going. And this is what I know about the wood. It's sitting on a piece of on a table. It's got a mass of 5 and it's sitting still. And then it's going to collide, and after those two things collide, I know that the bullet and the wood are moving as one object at a speed of 3 meters per second. All right, so first thing it asks us to do is determine the speed of the bullet before striking the wood block. Well, in that collision, you know, they told me that afterwards this stuff's moving at 3 meters per second. I know both masses. This is the mass of the wood. Sorry, this is the mass of the bullet, and this is the mass of the wood block. So I know all those things. This is just a straight up conservation of momentum problem. So momentum of this system, and by system we mean the bullet and the block. Okay, momentum of this bullet and block system before the collision. My lines seem to be straight, slightly crooked. Has to equal the momentum of this bullet and block system after the collision. And when we say after, we don't mean forever afterwards, because there's going to be friction and things like that acting on it afterwards. And so those provide external impulses that change the momentum of the system. We just mean from immediately before to immediately after. Okay, and I put this dot here so that you can see that the block moved from where it initially was. All right, so I've got my conservation of momentum equation here, that the momentum of the system before equals momentum of the system afterwards. I wrote out the momentums of each object within the system beforehand. So this is the bullet's momentum, mass of bullet, velocity of the bullet. This is the wood's momentum, mass of wood, velocity of wood. And then this is the total momentum of the system afterwards. And it's all moving at the same speed. So I took all that mass times the speed afterwards. Okay? And I'm trying to figure out then how fast the bullet was going initially. So I did my algebra steps to solve for the velocity of the bullet. And I found out that it's moving at 153 meters per second originally. So the bullet before it hits is moving at 153 meters per second. Okay, on to part B. Part B says determine the initial recoil velocity of the gun and person if they move together as one object when the gun is fired. So let's scroll down a little bit so you can see this a little better. Okay. All right. So now we're looking at a different system. Now we have a system that is a person and a bullet and a gun, all as one system. So this is my system, the bullet, person, gun system. Okay, and again, if I'm thinking about any forces exerted on this system, the only forces are going to be when the bullet flies forward. The gun is what pushes the bullet forward, or the expanding gases push the gun forward. Well, then that same stuff applies a force backward on the person and the gun. Notice this is clearly not drawn to scale. That is an enormous, enormous pistol if that's true. Okay, so in my picture I tried to label that little thing as the bullet. That's the bullet now. Again, not drawn to scale and apparently not flying in a straight line. I'm just not that good an artist. But what I know is that the momentum of this system of bullet, person, and gun beforehand has to equal the momentum of bullet, person, and gun afterwards. And so thinking about that, since all the forces again are internal to this system, what I know is that the momentum of this system also has to be conserved. So before I fire the gun, I've got written over here, my momentum for that system is 0. It doesn't have any momentum. Nothing's moving. So that means my momentum afterwards, the momentum of the bullet this way and the momentum of the gun and person that way, those two have to add back up to 0 because momentum for this system is conserved. Okay, and that's really the answer to C, is the explanation that, well, they have to go backwards if the bullet goes forward if the system itself of bullet, person, and gun started with no momentum. So my goal is again to figure out how fast the person, I just put person, but it's really person and gun. I just didn't want to write such a long subscript. So the person and gun are moving after the explosion. We want to know how fast that is. So I'm solving for that. I moved this bullet and velocity of bullet and mass of bullet to the other side of the equation. Okay, so I moved that over. Notice how I changed the sign. It's negative. And then I divided by mass of person plus mass of gun. And then my last step is to just plug in the numbers, and I get as my answer that the person and bullet are only moving backwards at 0.2 meters per second, roughly, negative 0.19 meters per second. That's pretty much it for this problem. It wasn't too bad.